Today we're going to use what we know about vector diagrams and apply that to the kinematic equations. Remember that a vector can be any quantity that has magnitude and direction. The magnitude is really the numerical value. The direction tells you where that number is going. Displacement and velocity are the two vector quantities that we are going to look at most when we're doing our kinematic equations. Here's an example of one without a kinematic equation, but just a quick review on adding vectors. So we have Tesla chasing his cat around the lab. The cat runs 5 meters east, 10 meters north, 7 meters west, then 4 meters north, before Tesla catches him. We want to know what is the cat's displacement. So when we see a problem like this, we have a total of 4 different vectors. But with those 4 vectors, really, all we care about is where he starts and where he finished. So the first thing we're going to do is separate them. And we're going to look at them by their direction. We have the east-west direction, and we have the north-south directions. I always like to make a quick table of these. So once we do that, and we assign north and east as positive, we have our 5 meters east, 7 meters west. So total in the northwest direction, in the east-west direction, we have gone -2 or 2 meters west. Looking in the north-south direction, you'll see we've gone 10 meters north and 4 meters north, giving us a total of 14 meters positive, or 14 meters in the north direction. Remember from the previous day's lessons that it doesn't matter where the vectors go on a grid. It only matters that their magnitude and direction are the proper size, length, and in the proper direction. So by finding the sum of all the east-west, we can find the total displacement in just the east-west direction. And then by finding the north-south sum, we can find the total displacement just in the north-south direction. Once we've done that, our problem becomes much simpler. We can draw our vector diagram, starting with just the 2 component vectors that we got from the problem. When you're drawing component vectors, you want to be very careful. You have your start, and you end up drawing your first vector. When you draw your second vector, you need to be careful that you start it where the first vector ended. If you don't do this, it'll be very hard to get the resultant. So as you see here, I have my 2 meters and my 14 meters drawn here. And that should be meters, sorry about that. Once we have our component vectors drawn, then we can go ahead and draw our resultant vector. Now the resultant vector is different than the component vectors, because what we care about in the resultant vector is that we need to know where we started and where we ended, and that's how we're going to get our displacement. So you'll notice the component vector will start at the start point, or the tail of the first vector we drew, and then we'll notice that it ends at the head of the second vector. The resultant vector can be easily identified by looking for the one spot where the 2 heads combined and the 2 tails combined. That's the key point of knowing where the resultant is. Once we draw the resultant vector, you'll notice that we have a triangle. Not only do we have a triangle, but we have a special right triangle. With a right triangle, we can find the magnitude of the resultant vector by using Pythagorean's theorem, which you can see the calculations over here to the right. The total distance traveled by Tesla's cat is going to be 10 square root of 2 meters. And then that is going to be, as the arrow shows, somewhere north and somewhere west. But we don't know exactly where. Doing Pythagorean theorem gets us the magnitude. But only the magnitude. So we need another step in order to get the direction. So finding the direction can be a little tricky until you get used to it. Here's a tip to show you how I do this. I look for my starting point. The starting point is going to be where the two tails meet, which would be right here. To make our life simpler, we're going to go ahead and imagine that we have a coordinate plane where the starting point is at the origin. If we put the starting point at the origin, then it's going to be simpler for us to determine the exact angle of the direction that our vector is moving. Now, really, we could put this triangle anywhere, but again, for ease of the problem, we're going to choose the origin. Once we choose the origin as of the coordinate plane for where our vector is going to set, now we can figure out which angle we need to calculate and where that angle is going to be located on the north, south, east, west scale. Looking here, we are going to choose the angle that is right here because it's inside the triangle and it is somewhere next to the horizontal plane. Now it becomes a simple step of trigonometry. If you remember from Sophotilla, if this is my angle here, 14 is opposite the angle, and 2 is adjacent the angle. So since we have opposite and adjacent, we can choose tangent as our sign to use. Now, could I use the resultant vector and use sine or cosine? Absolutely. However, to minimize human error, since the resultant vector was a calculated value and the component vectors are more exact, and we know those for sure because that was just simple adding and subtracting, I like to use the component vectors, and I highly recommend you do it as well. So if you remember how to solve the angle, it's over here to the right. Just type in tangent, inverse tangent of your opposite over adjacent, and then put that into your calculator to find out what the actual value of theta is. So you'll see that our theta is equal to 1.4. 1.4. Let's figure out now what direction that 1.4 means. So we are right here. Okay, classic mistake. I see 1.4. I look at my triangle. That makes absolutely no sense. So let's go ahead and check my calculator and find out that my calculator is in radians, not degrees. You want to make sure your calculator is set to degrees if you're calculating the degree of an angle. So try it again, and we get the degrees of 54.5. Makes a lot more sense. So 54.5 is right here. So here's west, and we are headed north of west. So my final answer is 54 degrees north of west with a magnitude of 10 square root of 2 meters. So actually probably 10 square root of 2 meters north of west. That's how you would solve that problem there. Now we have our total displacement. Okay, here's an example where we can use what we know about vector diagrams and kinematic equations. We have a park worker who's walking around picking up litter. It takes him 20 minutes to collect in 6 major areas of the park. He starts at the entrance and walks 15 meters east, picks up trash, then continues 12 meters south, then 6 meters west, 8 meters south, 10 meters east, and then